In this screencast, I'd like to discuss interaction effects, modeling interaction effects in multiple regression. Multiple regression, in its basic guise, its basic personality, is a linear additive technique. It assumes that the effect of each independent variable is the same at all values of the other independent variables in the model. For example, in the example that we've been tracing through this chapter, in the education battleground turnout example, multiple regression assumed that the effect of education on turnout, which we found to be in the multiple regression 0.55, is the same for battleground and non-battleground states. That's fine if you had an additive set of relationships, or if you're trying to ferret out spurious relationships. But if the effect of one independent variable on the dependent variable depends on the value of another independent variable, then you have interaction going on, and you have to figure out how to model it and accommodate that effect in the regression model. In multiple regression, we refer to interaction effects. An interaction effect occurs when the effect of an independent variable cannot be fairly summarized by a single partial effect. Instead, the effect varies depending on the value of another independent variable in the model. Now let's introduce a new example. This is survey data. I believe this is the American National Election Study. Think of a dependent variable measuring abortion opinions among a large group of respondents. The scale scores range from 0, this would be a respondent who took the most anti-abortion position, to 9, the most pro-abortion position. And so we're going to calculate mean values of this dependent. And we're going to examine the effect of party identification on these mean values. Independent variables party identification, it'll take on 3 values: Democrat, Independent, and Republican. The control variable here is political knowledge. This is going to be eventually modeled as a dummy, but it takes on 2 values. Respondents either are classified as having low political knowledge or high political knowledge. Let's look at a familiar friend first. This is a mean comparison analysis of this problem. Mean pro-choice scores by partisanship controlling for political knowledge. Let's look at the effect of partisanship among low knowledge respondents. Low knowledge Democrats scored 4.3 on this scale. It does go down, goes down to 3.7 among independents and down to 2.9 among Republicans. So if you were just summarizing the effect of partisanship for low knowledge respondents, you would say, well, the scale drops 1.4 points across the range of the independent variable. You know, is this going in the hypothesized direction? Yes. Is it a noticeable effect? Yes, it is. But let's compare that effect to the effect of partisanship among high knowledge respondents. Here, high knowledge Democrats are at 5.7 on this scale, drops to 4.6 among independents, and then to 2.8 among Republicans. So the effect here is twice as strong than it is among low knowledge respondents. So among high knowledge respondents, the effect of partisanship is 2.9. There's a drop of 2.9 points across the values of partisanship. You might also notice that the effect of knowledge for Democrats is rather pronounced. Democrats go from low knowledge to high knowledge. Their scale scores go from 4.3 to 5.7, over a point and a half, about a point and a half increase here. If you look down here at Republicans, the effect of knowledge is virtually nothing, 2.9 to 2.8. So the effect of knowledge depends on partisanship, and the effect of partisanship depends on knowledge. We have a lot of interaction going on in this data. Here it is graphically. This really tells the story, doesn't it? Here's that low knowledge line dropping about 1.4 or so across values of partisanship, and here's a much more steeply raked line among high knowledge respondents. So it's almost like when you reach into the data and switch knowledge from low to high, the relationship really becomes very well behaved and becomes quite a bit stronger. Let's figure out how to model this in regression. Now, here's the formal model. Y hat's going to be, of course, the estimate of abortion opinions. let's look first. In fact, let's look first at how these variables are coded. That'll give us a clue as to how they're going to behave when we manipulate their values. Y hat, of course, is the estimated pro-choice scale score. Partisanship now is going to be coded 0 for Democrats, so all the Democrats are going to have 0 on partisanship, 1 for independents, and 2 for Republicans. So this range of this variable is from 0 to 2 from Democrat to Republican. The high knowledge of dummy that's a dummy variable. It's coded 1 for respondents who have high political knowledge, and 0 for respondents with low political knowledge. So we've got a dummy variable in there. And when you model interaction, I've discovered it's always a helpful idea to have your variables scaled to 0, because if like Democrats are 0, we know certain terms in the model are going to drop out, and it makes it easier to interpret the coefficients. So A hat is going to estimate the abortion scale for low knowledge Democrats. Why is that? Well, partisanship is 0 for Democrats, so this term drops out. High knowledge is 0 because they're low knowledge respondents, and so what's called the interaction term also drops out. So sort of the base value is captured by A hat is going to be the scale score for low information Democrats. Now, in fact, for all low information respondents, we can use these linear additive building blocks to figure out the effects of first partisanship among low knowledge individuals, and then the base effect of the high knowledge dummy. Here's the difference. This is what's called an interaction term. Notice that the interaction term is going to take on a value of 0 for Democrats. It's going to take on a value of 1 for independents, and it's going to take on a value of 2 for Republicans. So this is a way of telling us, B3 is going to tell us how much to adjust the effect of partisanship when knowledge increases from 0 to 1. And here are the estimates, and the format for this table is actually what you're more going to be familiar with looking at a computer output. It's different from the other formats in this chapter, but this is a much more common way of presenting regression results. All right, let's see what we have here. The constant is 4.33. This then will be the scale score for low information Democrats because partisanship drops out. High knowledge doesn't occur because it's low information, and therefore the interaction term is also 0. Now, if we use the constant A hat and partisanship, which was a B1 in the model, we can figure out the effect of partisanship for low information respondents. 4.3, and then if you increase to low information independents, you reduce the scale by 0.7. To low information Republicans, reduce it by another 0.7. So it drops, as we found, about 1.4 points across values of partisanship for low information individuals. Here's that high knowledge dummy. A common mistake in modeling interactions is forgetting to put in the base effect of the interaction variable, the one that you think is causing the interaction. The base effect here is 1.5. This is going to be the amount that we add to low information Democrats. Why? Well, low information Democrats get 4.3. The partisanship dummy is still going to be 0 because Democrats are 0. And so 1.5 is going to be the boost in the scale score when you switch low information Democrats to high information Democrats. And we already saw that, I think, in the mean comparison table. High information Democrats are at something like 5.8 or roughly 5.8 on the scale, which would be those two. Now, here's the interaction term. The interaction term says that when knowledge switches from 0 to 1 and as partisanship goes up, you subtract an additional 0.76 points from the scale for each value increase in partisanship. So everybody gets the base effects, 0.433 minus 0.17 as we go up in partisanship, and then the minus 0.76 tells you how much more to reduce that effect. Looking over here, all these effects are very nice. We have relatively small standard errors. Partisanship has a strong t-statistic, minus 4.67, significant at 0.000. The same for high knowledge, that has a significant effect. And then the interaction effect also lights up. This is telling us that, the effect of partisanship for high knowledge respondents is significantly stronger. It's still negative, but it's significantly stronger for high knowledge respondents. Just to repeat, you use A hat and B 1 hat to estimate the effect of partisanship for low knowledge respondents. B 1 hat says to subtract 0.7 for each 1 unit increase in party, or minus 1.4 across the full range of party. So you subtract 0.7 as you go from Democrats to Independents, another 0.7 when you go to Republicans. So regression linearizes these differences. Use the base effect of knowledge, B2 hat, and the interaction term, B3 hat, to adjust the base estimates for high knowledge respondents. B3 hat, that's our interaction workhorse, says to subtract an additional 0.76 for each 1 unit increase in party, or across the full range of party, minus 1.52 across the full range of party. So 0.76 from Democrat to Independent, and another 0.76 from Independent to Republican. High knowledge respondents get the base effect, okay, so that we already know that partisanship is having an effect among low knowledge, plus the interaction effect, which is another minus 1.52. And of course, this works out very nicely when you add those effects together. You find the full effect for high knowledge respondents is minus 2.9. It should say these results match the differences in the mean comparison table.